Hello everyone. Today we'll start the lecture 11. This uh, this lecture is the introduction of the seismic analysis software, including the commercial software and the open source research software. And in this topic, I think it's quite useful in the practice engineer for the practice engineer. Most helpful for the structural engineer in the seismic analysis, including the dynamic analysis. I mean the including dynamic analysis means the wind dynamic analysis and the flow vibration. Also need some skill of this seismic analysis software. And today I will introduce some software in the market, especially in Hong Kong or main China. And in this topic, I will introduce several software, but actually in the market, there's a lot of software can do the seismic analysis. For example, in Hong Kong, I think Etabs and SAP 2000 is quite popular because it's user-friendly, especially the graphic user interface is quite user-friendly. And I think I will introduce the Etabs more because I will show you some operation sample in Etabs. And I think most of the software for structural analysis is quite the same procedure, so I will just only show one software like Etabs. If you have something information, you can check like a YouTube video. There's a lot of operation video about Etabs Step 2000 Midas, I think. And so let's get started to the introduction of the software. Etabs. I think this software is most used for the high-rise building. It has the concept, the story of the floor level. So you need to build a graphic in the story, and then you can easily build floor by floor. But actually it's in 3D, but you can model in 2D. So it's quite useful for the high-rise building because high-rise building we only focus on the plant, on the GFA. So we just focus on 2D drawing. Like we mark the column, mark the beam location, and the shear wall location. It's quite user directly to high-rise building. Okay, and the next software came from the same company called CSI Computer and Structure. So we call it the CSI. This company has a lot of wonderful software, including the Etabs for the high-rise building, SAP 2000 for some 3D structure, like a 3D steel structure, like a freeform structure, like a very fancy steel roof. I think SAP 2000 is much more powerful than Etabs, especially in the elastic analysis. But it's not convenient for build a high-rise building, but it's very convenient to build the freeform high-rise building, freeform structure like a long span structure. But they share with Etabs the same calculation core. Most of that, and I think it's quite popular used, especially in Hong Kong, the steel structure. Okay, Midas. Actually at the very beginning is made in Korea, but now today the main production center I think is in China. They focus on a lot of very advanced finite element analysis, and the user interface is quite friendly to the structural engineer. Is compared to some general finite element analysis software. And this one is quite the operation procedure is quite same as SAP 2000. When you get very fluent use the SAP 2000, you will very know how to use this software. And I think Midas nowadays is much more powerful than SAP 2000, especially in bridge design. So most of the bridge design and the civil design, including the tunnel, they use Midas. YJK and PKPM I combine together because these two software is mainly for the Chinese project or Chinese related project design. It's quite powerful, especially in the design precision. It can auto-gen the drawing, especially the RC detail drawing in the Chinese format, of course. It's very powerful in the member checking, but the calculation is not like it's much more like Etabs. It's floor by floor, but you also can build a very fancy 3D structure, but you need to take a little bit difficulty inside. Okay, and this four software, I think we also conclude that this four software we call it the elastic analysis software, including the static and the dynamic. So you can do a lot of analysis, including the wind load and the seismic analysis. And sometimes they can do like a thermal analysis for consider the temperature change. But actually, and this four is mainly powerful in the elastic design, elastic analysis, and they also have the design function according to some local code like Hong Kong code, Chinese code, and Europe code, and United States code. And so this four we also call is elastic. They means they very powerful in elastic analysis part, but in nonlinear analysis they just getting started, not very get further enough to touch the nonlinear part. And the Perform 3D. Perform 3D I think is most popular used in the world, the nonlinear software for the commercial, especially the structure, the building structure. And this software contain a lot of macro element, means the element just use a little seldom degree of freedom to simulate the nonlinear behavior. I think you guys may be not quite familiar with nonlinear analysis, but I will introduce in the next lecture. In this lecture, I will focus on the elastic analysis software. So Perform 3D, I will teach in the next lecture, because when you learn how to proceed the analysis procedure in the elastic analysis, you will know how to do the nonlinear analysis in the next step. So you just know this software for remind this software can do nonlinear analysis. So all the material can be nonlinear. And this is commercial. So the other software we call OpenSys. And actually this graphic input, this graphic GUI of this OpenSys software is not real. It's just a company called like Next FEM. No, this one is GID. GID we just a general graphic input for the all types of the finite element analysis software. And this one is just the graphic user interface development, secondary development for the OpenSys. For OpenSys, this software there has no interface at all. They just use like DOS, command DOS language, just type in the keyboard, and you can type a long list of the command code, and then transfer to we call it the TCL language, and then run this or like a script, and then have the analysis result come out. It's just like a black box. It's the graphic is just like command DOS graphic input. It's just a text input. So it's not user friendly, but this is very powerful in the development. A lot of research use this one, and most of the reason is this software is open source. This is not the commercial software, and all the other one is commercial software. This one is the open source analysis software. It can run nonlinear analysis, and it's free. You don't need pay any money for this software. You can download and use directly. And this software, because it provides all the source code, so you know how the computer modify or how the computer simulate the nonlinear behavior of the concrete structure or steel structure. You can look inside the source code, so you know the theory inside, and you can write the new element or new material, nonlinear material inside this platform. So you can do a lot of high-level research, like a lot of PhD, do a lot of structure analysis, advanced research in this platform. Because you just need to build a new material, new element. You don't need to build a whole system or whole platform for the nonlinear analysis. You just develop one key part to add in this software, and then you can run the analysis and see the result. So this is powerful in the research. If I have time, next lecture I will introduce this software, especially for some student maybe will go to the PhD study in the future. And ANSYS is a very classical finite element analysis method program. It's very early to use, and sorry, this is Etabs, I think. This is ANSYS. The label is wrong. And ANSYS is the classical FEM. We could just call FEM for short. FEM software for the including the nonlinear analysis, linear analysis of course, and seismic, dynamic analysis, static analysis. And the software includes much more because it's not only focused on the mechanic or called the structural part, including the thermal, electricity, magnetics, electricity and magnetics, chemical, and fluent. Fluent means wind and the water. All the finite element method can do inside. So most of the user, I think, is the mechanical researcher, and the other one is some high-level engineer in every region, like structural engineer, like a mechanical engineer, like even the airplane engineer, who knows. So most of these engineer will use finite element to analyze some very critical problem before they do the very expensive real product test. So they will use this product. So in the research area, I think structure will use this one because they have lots of very nice finite element model already built inside and very stable. It's just like the Abacus. Abacus is much more developed fast than the ANSYS. Is much more popular nowadays. Most of the researchers do we call it the micro element analysis in concrete. Concrete structure, you know that because there is a rebar inside. For example, you want to study the rebar and the concrete relationship inside one member. Even you want to study how the rebar have the bond effect with the concrete surface, you need to look very detailed into the dimension. So you need to use the very small element to model this structure or this component. So we call this one is the micro element method. So you need to mesh like this one, a single beam. You need to mesh like 1,000 of the little block, and you can see that this degree of freedom should be a million or 10 billion. It's a very large model. So we run this model, you need some time, especially if this model is a nonlinear model, you need like several days for the PC. If you need to make it faster, you need to run in the very big computer like a refrigerator computer. So this is the very fast introduce for this software. So you know that this in most of the, because you know that finite element research is very need to pay a lot of money in the research. So most of the software nowadays is likely is commercial software. Open source software is quite small. Small people will do this. But OpenSea is open source, but they're not, of course, because open source, so there's a lot of not user friendly and a lot of problem inside. And finite element, I think most of the researcher will use MATLAB to build their own code inside the MATLAB system. So MATLAB also you can see that it's a finite element method, so you also can do some dynamic analysis. Some of the textbooks have a lot of MATLAB source code to run the dynamic analysis. I can search if I interesting. I will send you some reference. Okay, and the next stage we will talk about how to. This is the practical part to introduce how to model the structural model in the seismic software. Okay, before we start the practical analysis of the operation for this seismic analysis software, I will introduce the procedure or the key point or the key nums for this part. We focus on this equation. This is the structural dynamic or seismic analysis basic equation, and by the acceleration plus the damping constant by the velocity plus the stiffness by the displacement or deformation equal to the external load. And this Dirichlet equation is a basic core for the seismic analysis software. So all the procedure, all the keywords for the model for the analysis software is follow this equation. You can see that. Actually, at the very beginning, we need to build the model. For example, in this course, we use the Etabs, for example, to use the graphic user input to build like a draw the structure in the screen. So we just need to build the model first. Build the model means you need to define some material property, elastic material property, and the section property and the geometry. And these three key things, it will determine the structural stiffness. Is from the K matrix. K means stiffness matrix. And the second part, you need to define some load like the dead load and like the live load. You combine this dead load and the live load to be the mass source. Mass source, it means to transfer to the mass. Mass means every node had their own mass, and to form this mass matrix. Okay, so you need to define the mass source. Most of the case, the mass source is come from the loading, so we need to define the loading, especially the gravity loading. So the third one is the damping ratio. Damping ratio in the graphic input is quite easy. You just need to input the damping ratio for the system, like a steel structure. You need to input some like a 0.02 damping ratio. For the concrete, maybe you input the 0.05 damping ratio for the seismic analysis. The fourth one is the dynamic load. Because we need to introduce this part like a single degree of freedom system, maybe we need to add the harmonic loading to excitate the structure. So we need to introduce some dynamic load, how to input the dynamic load for the structure, especially in the example of the single degree of freedom system. So the fifth one is the ground motion data. Ground motion data, you need to know how to modify this ground motion data. Most of them we call it the ground acceleration data. So in most of the case, we just need to input the acceleration of the ground. No need to input the actual displacement or absolute displacement of the ground. Seldom use this one. So we just need to input the acceleration data. So acceleration data, you need to know how to modify the time step, how to sometimes the ground motion is too long, you need to cut it short. So you need to focus on how to cheat the data, especially the scale factor. Sometimes if you just want to scale the ground motion data before you input, you just need to do some Excel work. So maybe I will introduce how to use Excel to look into the data. And most of the time you need to know the peak acceleration of this data. Okay, and this is 1, 2, 3, 4 parts, including the input and the output, the equation. So this is from the K matrix, mass matrix, damping matrix, and this two part is introduce how to input the dynamic load. So ground motion data, you transfer the acceleration data to the external load. So the sixth part is follow the lecture 3 or 4, the model analysis, including the single degree of freedom system and the MDOH system. So you need to how to press the button only. It's just very easy. But some cases may be focused on some setting, especially in Etabs, this software. And the 7 is time history analysis. I will show you how to run the time history analysis. You can compare with the assignment or the example you do before by hand calculation, especially for the single degree of freedom system. In the last part, we will talk about the spectrum analysis. The spectrum analysis, I think we will introduce two parts. One is use the equation, like the Etabs that have several country code, the equation of the spectrum. And the other part, we will import the spectral shape of the spectrum to run the analysis. And the ninth part I done right here is how to see how to check the model and how to check the result. Is it correct? So I will start. I will end this presentation and transfer to the Etabs operation. And this part is the software I already introduced to you and give all of you the source code. You can look into how the program to run these several items. Like I have two programs for the single degree of freedom system calculation. One is the free vibration, and the other one is the forced vibration for the single degree of freedom, harmonic vibration. And you can use this one to do your assignment. And the other one, we just introduced some Harmonic integration for the single degree of freedom system. You can use this one to transfer the acceleration ground motion data to be a spectrum curve. So, and you can use this one for the MDOF system calculation in the certain position. And model analysis is I already give you this program. You can run the recorded one is the story stiffness model, and this model only consider the shear stiffness like a frame structure, and then you can input every story's mass and stiffness, lateral stiffness, and then you can run all the mold shape and check all the period. So in this several program, you can use like Etabs Step 2000 to build a model to compare with this program. Also, you can use your hand calculation to check the program is it correct, or you can use the program to check your hand calculation also. And by this procedure, you know two things to learn. One is to learn how to verify the result, and the other one is how to make sure you know how to operation in the software. So I think I encourage you to do this part to verify hand calculation and the computer analysis. So now I transfer to the Etabs operation introduction. Okay, start Etabs program. And this version is 9.7, and now in this I will for example here. In this part, I will build a single degree of freedom system first to make sure understand the whole procedure of how to build a model. So at the very beginning, we need to transfer the unit system to be the Newton mm, and we need to build a new EDB, means to build a new file. So this is the floor and the grid line, and actually very beginning they will allow you to build a grid line. I just need to build a single bar, like a single degree of freedom system. So I build a simple grid. So I transfer to the elevation. In this graphic, you can see that they already built a cube system for the grid line system. And then we transfer to use the elevation. For example, we cut the elevation 1 here. Elevation 1. Okay, in this elevation, we can build a single bar model. For example, I need to check the material first. So check the material like a concrete. We input the correct module of the elastic, like 330,000. And you should remember these elastic modulus. I can check in the Hong Kong code. So the weight and the mass here I will input 0. We will not consider the part cell weight to make sure this system is the single degree of freedom system. Request OK. And then second part we build this 3 part is the material section and the geometry. So we build a section. So we build the square column, for example, like a 400 by 400 square column. So in this one, we already built is you need to define the material and the dimension because it's the rectangular section, so we need to input the depth and the width. Okay, the other section you can delete, if you want. Okay, you focus on this one, C 400 by 400. Okay, and then you can press here, draw lines, and then you just draw one line. Make sure the bottom is fixed, so it just had 1 degree of freedom, 1 point can move. But actually, this we already know this is a 3D system, so each node has 3 dimensions can move. You can see here our side, the joint, and the restraint. You can see that can translation in X direction and the rotation about X direction. So it has the 6 degree of freedom for each node. So we need to transfer to be a single degree of freedom system. We just need to allow X direction can move. So now we assign this one has only X direction can move. So this system is the single degree of freedom system. So we can run the analysis based this one. When you finish the model, they all have the system will give you the structural stiffness metric, and then we can run the analysis. We cannot run because we have not yet applied the mask. So we need to apply the mask. We apply the mask as we can see the picture. We just apply to this node or this joint. So we assign joint the point mask here, additional point mask. So in X direction, because the X direction had the movement, so we just need to assign X direction had the mass like 20. In this Newton mm system, 20 means 20 ton. So press OK, and this is the mass. So we only have the stiffness matrix. When we have the mass matrix, we can run the model analysis, even just one single degree of freedom system. So we need to set the dynamic analysis option. So come to analysis and check here, set analysis option. Okay, in this system, you just no need to press different because we already set this one have the X direction translation degree of freedom. So we just need to click the dynamic, set the dynamic parameter, and just write 1 because they only have 1 degree of freedom, so we just have only 1 mode. So the only 1 mode has the only 1 period, only 1 frequency. So press OK. You can run here. You can save the name of the structure of this sample, like model 3, for example. Okay, finish, and then we can press the show model shape. You can see this one is just show that the mode 1 is 0.0971 second, and means it's successful to run the model analysis. And when you want to see the next mode, you cannot see because we have only 1 degree of freedom, so we have only 1 mode. So finish the model analysis. And this part is quite easy, but you just can verify by your hand calculation for this one. So the second step is we need to do the harmonic vibration analysis. This part is you need to define the X dynamic load. Dynamic we use sine or cosine function to define this force. So we need to know we need to apply the force. Unit force, like a 1 kN, mean the P0, type here. For the equation, PT should equal to P0 by cosine or sine, for example, cosine omega by t. Okay, so this is if the equation, the function, the maximum value of the function is equal to 1, and this is the amplify factor. So you can assign here. So we define a load case. We can press define static load case and define P0. And of course it's other load and they contain the cell weight only. Okay, and then we define the loading. So assign the point load here, joint or point load, and we assign like 1 kN only. Okay, and this is the loading of the P0, and you need to define the function of the cosine omega t. So we transfer to here. We define the time history function, and can see cosine and sine is here. So for example, we need to define cosine function, for example, and cosine function is here, and this is you need to input the period. So period, you can see here, we need to input this omega, but actually most of the software is need you to input the period. So period equal to 2 by pi minus 2 by 5 divide omega or over omega. So we need to transfer the calculation for this one. So I'll give you an example. For example, we need to 0.04, for example, the period. And this is the number of the circle, number of the step per circle. 20, I think is enough. And this is the circle. For example, we need to 20. Then check here the last step. It's like 0.79 seconds. I think too short. At least with maybe 5 seconds. So we need to input like 200. Or it's too many. So we can input like 50. Okay. Oh, so many steps here. So this is we call the function one. So the period, the function is 0.04 seconds. Press OK. Okay, and then we will define the time history analysis case. In this definition is quite difficult. In this part, we need to define the damping ratio here, like 0.05. This is a damping ratio. It refers to this part, damping ratio. Okay, and then we need to input the time step for the time history, like a 5 sec, like a 0.02, and like a 2000 slab, 0.02. Like this one, how many time duration for this analysis? We just multiple by these two things. 1000 by 0.02, it means 20 seconds. We just don't want so long. We just want 10 seconds, like this. If we use this one, it's just 5 seconds. Okay, this is 5 second analysis. And this is the function, this is a scale factor, and we don't use the acceleration because we use external load, so we use P0, and this is the cosine function, and this is the scale factor, so we press add, can run here, then we press OK. And the direction we think is in X direction because we apply the unit force in X direction. Okay, and then we can run the time history analysis. Okay, after the analysis, we can check the result. We can show the time history data of this deformation. We can press the display and the show time history trace, and press the define function. We select the joint 1, and we need to show the displacement in X direction. Press OK. And then we can show the time shift. We show the 0 to 2 seconds because the time duration is short. This is the result of the high frequency vibration. we can see that at the very short time is like not steady result. After a certain time duration will become the stable result. So this is the steady stage, the result, and this is the including the free vibration here. So, and this is the result of the displacement. We also can check the shear time history data of the shear. For example, we select this member and display show time history trace, and just select the frame column 1. Show this data. We just want to see the 2-axis shear. And you can see the local axis here, 2 or 3, I don't remember, but we can try here shear in 2 directions. So we can see this one. Yeah, this is correct. Can show 0 to 2 seconds, and this is the shear force time history for this member. You can also consider as the bottom shear, somewhat the same. And this part is finished. We just know how to run this analysis. Actually, we'll see the very lucky result here because we can show the time history. You can see here. You can see that it divides 2 parts. One is the unstable result for at the very beginning of the harmonic vibration. After this part, we can come to the steady vibration under the harmonic vibration loading. And after that, when we shut down the external load, the external becomes 0. It will become the free vibration, and the free vibration it will become smaller and smaller, and then become to 0. And this part is we call it the free vibration here. So you can see we including free part when we apply the loading. Okay, and this part is quite easy, but I think in this part we'll know how to run the single degree of freedom analysis. You can also compare with this small calculation program. You can see the difference between these 2 parts. Also, we can check the different external loading frequency will have the different result for the structure response. And this part is very easy, so I will transfer to the second part. Second part will build the 2D and the 3D, or even the 3D structure. I think most of you will consider how to build a 3D structure and compute the time history analysis for this one. Okay, I will start the 3D model for the Etabs in the Etabs platform to build a several-story frame structure in Etabs, and run the spectrum analysis, time history analysis, the model analysis in these 3 parts. Just show you how to operation in this software. And Etabs and SET 2000, they have lots of YouTube video. You can search online. There are a lot of videos to teach you how to build a structural model, but they quite focus on the operation. They seldom introduce the theory inside. And okay, we'll see how to build like a 8-story frame structure. Just press here 8-story. Okay, we just build a structure like 3 or 4 grid line by 4 grid line here. Okay, in the very beginning, you save the model first. The model 4. Okay, and so we need to modify the grid line because we need to show you how to build the structure by any type of the grid line. Here we can just edit the grid data, global, modify, like a first grid, I transfer to spacing, like an 8 meter, 6 meter, 8 meter. Okay, and just focus on this one. And we need to define the material, like a concrete. We call it D30, for example. The mass 2.5, the weight 2.5. We need to compute the cell weight. Okay. Need to build the frame section. In this part, we build two sections. One is for column, one is for beam. For example, for the rectangular beam, this is 400 by 600 rectangular beam. The concrete material is V30. Okay, and then we need to build the column here. This is the same procedure for the beam. C 400 by 400 is the column. Okay, we can use this one to build a column. We can build in the grid line. Okay, assign the real section like C 400 by 400, and then we build a concrete beam. Okay, and here we need to define some slab section. For example, we need to slab 120 thickness. We use membranes and this one. Okay, and we assign the slab. Okay, and then we assign the dead load and the live load for the slab, and the dead load is 1.5 kPa and the live load is 1.6 kPa and no 2.0 kPa. Okay, and be careful when you input the loading. The unit is quite important. Try to input the correct unit. And the second part is when you finish this part, just one story, we build the member and the loading and the slab. You can see the 3D view here. So, and then we can replicate this floor to be all the structure. Okay, edit and replicate here. So we can copy to story 7 to story 1. Okay, the whole model is finished. You can see the extrusion view. Yeah, it's like here. Okay, and then we just double check the support for the column button. And in Hong Kong, I think this is correct. We most likely use the pin support for the column. And then we just need to check the mass source. So we just described before, the source is come from the loading. For example, in this case, we checked from loading, and the dead load is 100% and the live load is 50%. Okay, in this part, we just focus on this one, including the lateral mass only. When you click, it just only provide every floor has only 2 direction mass, including the including the rotation mass. But for the vertical vibration, it cannot consider, because vertical vibration need to have the exact direction mass. So when you click here, unclick here, you can run the vertical vibration. And this one is a lump lateral mass at story level, means the mass only happen on the story level. If you divide the column into several pieces, they will generate the mass in the middle of the column, but it will have no mass because the mass will generate to the story level. So focus on these 2 settings. In this case, we just need the lateral mass, so we need to click here, hit both this one, press OK, and we finish this part. We call it here define the mass. So, and when we have the stiffness matrix and the mass matrix, we can run the run the model analysis, because this is the NDOF system. Even is A story, it at least more than A DOF, so it's a lot of DOF. So we can run maybe thousands of the hundreds of the model, but actually we just need quite a few. So we need to define the analysis option, check the dynamic analysis. We can input a lot of like 1200 mode shape, but actually we need to put several. Make sure they had the 90% of contribution. For example, we input 12, press OK, and actually we can press run. Okay, you can see that they have the static analysis for the dead load and the live load. We press here to show the model shape like a single degree freedom system example. You can see the vibration already checked and show the first mode or first period is 1.5 seconds. We can press the star animation and so we can see the mode shape. We can, from the top view, check the video view, XY is 0. You can see that this is the top view of the building structure. You can see the first mode is vibrate in X direction. Okay, and the second mode is vibrate in Y direction. The third mode is torsion, and the fourth mode is X direction, but it's in the second mode shape. You can see the elevation. This is show the elevation. I think it's another direction elevation. Okay, you can see that it's like a second mode shape, but in the global is the fourth mode, but in X direction is the second mode. The third mode is another direction, the second mode, and this is second torsion mode. And you can see that mode 7 become the X direction third mode. So you can check the mode shape. And Etabs is very convenient to export the result. We can use the show table function to show all this period, like period, mode shape, and the contribution factor. We can look into the detail because most of the information we already teach in the previous lecture. We just give you the theory calculation or hand calculation. So we can see how to compare the real structural software, and you can see the show table. We click analysis result, the model information. You can click all here. We will describe this output result to you, and we just press OK. And this is the analysis result. You can see that this is the model participation mass ratio. So you can see different mode shape here. So the first mode is 1.56 seconds, second mode 1.5. This is the mode. You can see this one is the mass participation ratio, means how many mass will contribute in this direction movement. For example, in X direction movement, the 93% of the mass will contribute. So it means in this mode, most of the mass will contribute the Y direction. And you can find that the second X direction mode is here. You can see that only 5.5% will contribute to the first mode. So in this concept, it means when you run the time history analysis, the contribution for the first mode is likely 93%. In the calculation we just described before, we use the model superposition method to compute the time history analysis. We already described the contribution, the meaning of this contribution. And this is the model participation factor. You can see that it's almost the same. You can see this one. We can show this one. We can see that this one is the in X direction. They have 50% of the contribution. So it most likely means you can compare this one X, Y, and RZ, and RS and RY because of the torsional effect you can ignore. You just for the story model, you just focus on the x direction, y direction, and the torsion direction. You can see that in these three values, you can see that the x direction movement or the x direction translation factor is greater compared to these two parts. So it means it's the x direction vibration shape. So you can know that this is the x direction movement shape model, and this is y direction, and this is torsional. Because compare these three results, we know that this part is quite critical. So, and for the frame structure or for the regular structure, the best of the distribution for the mode shape is x direction movement or y direction movement. It doesn't matter. The one direction movement, and the one direction torsional movement is for the third period, and the second period is a repeat, and the fourth period is movement, and the fifth is movement, and the sixth is torsional. And this is quite common for the regular building, but we need to focus on control the torsional will not become the first. This is the most critical option for the seismic analysis. Okay, and in the next part we will try to import the ground motion to run the time history analysis. So we transfer to the Excel calculation. Excel operation for the ground motion. So this is the ground motion of the certain earthquake. I think the name of this earthquake is EL Central Earthquake Ground Motion. We just create a new Excel table. We just copy from the notepad for this file. We just place here, and we just draw this picture of the time history. You can see that most of the earthquake time history is no meaning for show the time history record. The only meaning for display this curve, I think, is to cut the duration of this earthquake. For example, if the computer is quite slow, you need to get the maximum result. You can use to cut the duration. For example, we cut like this one is 25 or 28 seconds. We just cut here, cut 50 seconds. We cut the ground motion, but actually it's no meaning because we can set in the time history analysis case. So in this time history, the time step is 0.2 seconds. So we can multiply by here one. We can see that it's like a 50 seconds, and we cannot see the maximum value by use this curve. So we just can use Excel function to get the maximum value. So actually, we need to get the maximum absolute value of this timesheet data. So this is the maximum value, and the minimum value is here. So we can see that the maximum absolute value, absolute value for this cell and this cell, the maximum value is quite obvious, is here, 0.356. No matter, because time function has no value. We need to focus on the target acceleration. For example, in this structure, we need to input like 100 gal. 100 gal means 100 cm per second square. Okay, and so it means 1000 mm per second square. So we need to scale this time history. You can use Excel, also you can use the Etabs to scale, but you need to know the scale factor. So we need to use this target acceleration to divide the peak acceleration in this ground motion data. So the scale factor, here scale factor equal to 2801. So we need to copy this data to the Etabs. So we open the Etabs. We need to define the time history. function. So ground motion data most likely is from the file. Cannot use the equation, so should be from the file. So this is the function one, or we can hit one. For example, the time step we mentioned before is 0.02 second. We browse the location of the file. Just copy the dictionary, copy the folder address for this ground motion. Because we cannot see because the data is here. The format is text file. So to press the GM1. Okay, we can describe and display the graph like Excel. So we can zoom in, check the maximum value. It's almost the same as the Excel. So here is finish the input for the time history. Don't forget to press OK. Press OK. Okay, we need to define the acceleration, the ground acceleration in the time history case. We add the new time history case. This is the time history case. We can change like the GM1, ground motion one. And the damping ratio input here, like before. We just press the 0.05 second, for example. And we run 20 seconds. The time step is 0.01. So it's 20 seconds. So, and this one, we just, for example, in this direction, we apply the X direction earthquake. So we in X direction. So it's acceleration direction 1 means X direction acceleration. And the function name is hist1, and the scale factor, which I copy from this Excel. This is the scale factor. Right time should be at the very beginning, so it's 0. Angle, this is the angle of the excitation. Because we just input the X direction, so it should be 0. So we add here, we press OK, and we finish all the define for the external loading or the dynamic loading. So we can run now. We can run the time history analysis. So we had the integration of 2,000 steps, and in Etabs, I think it's used the model superposition method to compute the result. So if you need to run this one, make sure the model analysis is okay, and we can check the result now. For example, we can show the displacement. For example, we check the rooftop is 8th floor, like this angle. We can show the time history data. This is the rooftop displacement. Join 1 is the story 8. Check the displacement. Okay, you can show the displacement. Okay, you can see that this is the displacement of the result. If want to export this result to build the Excel table, you can use print table to file. You can export to the file. For example, I'll show you how to do this one. And we just export to like this is the top displacement dot text. Press OK. Okay, and here we can show that this is the time history data, including the time and the time step and the result. The join 1, the X direction displacement. You can put in Excel. You can use the data and split the data by the space thing. Okay, you can select these 2 column data to draw the Excel graphic. So this graphic is almost the same compared to the result of the Etabs. So you can use this one to print out the result report for the report. Okay, and also we can check the base shear. For the structure, we need to check the base shear, time history data. Also, we use this one, show time history chase. Okay, we see the column. No need to select anything, and we need to show the base shear. So base shear is the base function and the base shear x. Okay, and just plot the base shear x direction, and this is the base shear time history data. Okay, most of the case we just need to envelope the displacement. For example, we can show this is the mode shape. We show the time history displacement, but actually in this time history data you can input the time, exact time, but we don't want to show the time, we just want to show the envelope. So we can use the locum here, node combination, add new locum, and then we will put the time history, and this one we just use the envelope. Okay, so common is the envelope, the time history. We can use the x direction view to see the deformation, the maximum deformation of the frame structure. Okay. Okay, see the correct proportion. Okay, we can show the displacement. We just not show the time step second by second. We just show the combo one here. This is the envelope. So we can capture the envelope displacement. Is the rooftop displacement is 41 millimeter. You check the result here, like 41 here, same. So we can also show the shear member axial force for the envelope. For example, axial force. You can see the envelope like here is two color. One is the light blue, one is the dark blue. It means the maximum negative maximum and the positive maximum for the axial load. Also, you can check the moment envelope here. So it's quite user friendly when you want to check the result. Okay, and this part we just described is how to run the time history analysis. So the other part for the seismic design is spectrum analysis. For example, we need to use the function to form the curve. We can use the spectrum here. You can see define response spectrum function. So here's a lot of functions from different country code. For example, Chinese code, and different Etabs have different version for this one. For example, we need to spectrum 7 degree. This is the damping ratio for the spectrum, not for the structure. And 7 degree of the earthquake should be 0.08, and 0 degree 0.1 G. This is the medium earthquake level, and the character ground period 0.35. This is considered the partition wall contribution for the stiffness. We will reduce the period, so we input some factor like a 0.9 to modify. There's several percent of the partition wall will contribute the dynamic stiffness for the structure, so we'll reduce the structure period. So after reduce the period, the earthquake level will increase. The earthquake force will increase by reduce the period of the structure. So this is the factor we need to input when we have a lot of partition. Because this is a low-rise building, there's a lot of partition wall. We input the 0.85. So we can generate the spectrum by using this formula, and then we press OK, and this is by equation. Press OK. Okay, and then we will run the spectrum analysis. We need to define the spectrum case. Okay, we add the spectrum. So remember, this is the spectrum case, not the spectrum curve. So we need to divide this spectrum in different direction. For example, we have spectrum X direction and Y direction, even the 45 degree direction. And this is the model combination method. Because it's a 3D structure, so you use CQC method. Consider the torsional mode shape. But actually, in the previous lecture, we just only introduced to you the XRSS method to compute the spectrum analysis. But because we had introduced to you for hand calculation, so it only had 2D model. For a 3D model, we need to use CQC method. So, and then we use SSRC for the direction combination. And if Chinese, we use the modified SSR. And we use the 7 degree of the spec 7D for the X direction spectrum. Before we input this scale factor, which I introduced to you the spectrum for the Chinese project. The spectrum for different countries have different definition. For example, in China, I show you this curve is much more convenient. Just press OK first. Show this curve. Some of the curve. This is time history. Show you the spectrum curve. Some curve, the p-value here is the acceleration factor. Some is the acceleration itself. So in Chinese spectrum curve, the p-value is the acceleration factor. So what do you mean the acceleration factor? It means this one, it should be applied the g, the gravity constant g, to generate the acceleration. So this is the factor, so it had no unit, not the acceleration. So in the spectrum, we need to input the g constant. For the unit is mm, so the g is 9810. This is the g when the unit is in mm. This is the gravity constant. So press OK, and we can introduce the other part. For example, we need to input the two direction earthquake. We use SSRS 7D because two direction. We need to input the U2 direction factor. But this one, because it's a second direction, so we need to use this combination, the 0.855. This one. This is according to the Chinese code, to reduce the second direction p-value. So this is two direction earthquake. If we input the earthquake, consider the 5% of the eccentric ratio. We just input the one direction earthquake. After that, we need to put here 0.05, the ratio of the eccentricity. So it means the eccentricity means when you apply the earthquake load, the mass source is in the center, so the excitation of the loading, the point load or the mass load, it should be in the center. But in the diaphragm center, I mean. But if we consider eccentricity, the loading will have a little bit eccentricity to cause the torsion. Because when you apply the single direction of the earthquake, we will have no torsion. But when you apply the loading, consider the eccentricity, you have a little bit torsion here. So when you want to consider the eccentricity, you just need to put the eccentricity ratio here. So in this case, we just put 0. We just want to run the single direction earthquake. Okay, and then we run. So this is a time history case, and the spectrum is like a static analysis, quite so fast, you cannot see the result, the running position. So you can see the X direction, and this is X direction. Okay, so the spectrum movement. So you can see this is the X direction movement. You can see the member shear, like a movement. It also had the maximum value and the minimum value. Because we use like a CQC or SSS method to generate the force, so it only had the value, no direction. So you can see the maximum value and the minimum value. But you can see this value is the same, the maximum and the minimum, because it only have the absolute value for the member. And this is the spectrum analysis setting. And if you have time, you can input the spectrum curve by the formula. You can modify the spectrum. For example, I transfer this curve to some spectrum. This is generated from the equation. And okay, and then we export this spectrum function curve, modify, convert, describe, show the curve. It's okay. We can show exactly the equation, the function curve for the spectrum curve. This is all the input of the Etabs. We can show the database of the function. I think it's the function here. Okay. So this is the function. We can copy this one to the Excel table. And this is the period, and this is the acceleration factor. You can see the curve here. So this is the format of the user-defined spectrum curve. For example, I transfer this one to be a text file here. So name it text, the spectrum user-defined spectrum dot test. Just paste here. There are two column data. One is the period, the other one is the acceleration factor. Okay, and if we want to import this spectrum, we can use this function, spectrum function. And in this part, we don't need to use the country code. We just input our spectrum, because for understanding, after several years, Hong Kong will publish the seismic code. I think in the short time, there had no commercial software for the Hong Kong code to calculate the seismic analysis. So you need to, most of the case, you need to import the user-defined spectrum curve to the computer. So we just use the user spectrum. And then here is the input the period and the acceleration, but it's quite slow. We just can use it from the file. Okay, this is from the file. We can call the user spectrum. This is the temperature, and the file name we browse. Put in the desktop. User defined test. Here, user spectrum. Okay, this displays the curve. Okay, we see that is the period and the value. Yeah. So we can see that period and the value can show the curve like we just put in the Excel. So we press OK. Okay, we successful to put the user-defined spectrum curve into the computer. So, and the Etabs operation is finished. So you can practice in your own computer to maybe to run some frame structure or shear wall structure, time history analysis, seismic analysis, spectrum analysis, and the model analysis, and they run the whole procedure. And you will maybe you just verify some hand calculation, especially some our assignment. In this year, I think the examination will cancel and will give you some extend assignment as the examination. So some of the questions I think you can use computer to verify. So I think this lecture and this video will help you to understand how to build a model in the software and run the analysis. And this whole lecture is introduce to you how to operate and certain theory embed inside in the operation, but all the theory here is in the elastic theory. So we come to the PPT. But actually nowadays, especially for the seismic design, especially in the research stage, most of the analysis should be the nonlinear. So for Fun 3D, OpenSeas, even Abacus, they will need you to study because in the future most of the project will imply the nonlinear analysis. The most reason is the computer technology is improved, so the calculation cost is including the money and the time is become cheaper and faster. So the nonlinear analysis will become the major method to run the seismic analysis. So maybe in the next lecture I will introduce to you some real practical method to run the nonlinear analysis. For of course, because of the short time, I think we'll give you the intensive introduction of the OpenSea and run the simple structure. And OpenSea has a lot of learning material on internet. You can go to my website. There's a lot of OpenSea sample, but most of them in Chinese. It doesn't matter. And you can also go to the OpenSea Berkeley. This software is OpenSea is developed by the University of the Berkeley, and it has a lot of information, including the software and the sample here, and most of them is nonlinear analysis. So you can learn by yourself in this website. I will give you the introduction of the OpenSea in next lecture for the nonlinear analysis part. Thank you for watching this lecture video. If you have any question about the assignment, you can ask me, and then we'll see you in the next lecture video. Thank you. Bye bye.